Hello, my name is Olusegun, but you can call me Shegun. I'm an electrical engineer and data science enthusiast. Although I currently work in an engineering role, I'm involved in freelance and volunteer work in the data science field. One of them being as a volunteer here with Statistics Without Borders, SWB. In this module under the biostatistics subject, we'll be discussing the Poisson distribution. Yes, Poisson is a French word for fish, but are we really discussing fishes here, the distribution of fish? As you can see in this cartoon, it says, my husband always loves your Poisson distribution. There we can see fish being distributed on his stand. So are we discussing that? Well, of course not. Actually, Poisson was named after the French mathematician Simeon Denis Poisson, and he was credited with developing the Poisson process and hence the Poisson distribution. So that has been cleared up. Now we move into the slides themselves to discuss the Poisson distribution. So here are the slides, Poisson distribution, lesson 1 by Olusegun Inetianbor. That is me. So the agenda for this module, there are 6 actually. The first agenda is the theory of the Poisson process. There we discuss in more theoretical detail what the Poisson process is all about, the Poisson distribution itself, and certain criteria that can be used to describe an event as a Poisson process. In the second agenda, we discuss the Poisson distribution formula. So the Poisson distribution can be described by a mathematical equation. What that equation is, we'll find out in that agenda, and through some worked examples, we know how to apply that equation. In agenda 3, we discuss use cases of Poisson distribution in biostatistics. This is indeed the biostatistics subject. So in this module, we'll apply Poisson distribution to biostatistics. We'll see a use case of it and some other examples of biology that can be called the Poisson process. In agenda 4, we discuss the waiting time concept. What that is, we'll find out on that slide. And in agenda 5, we discuss some exercises to test our knowledge of this module. And in agenda 6, we summarize the whole module, Poisson distribution. So on to the next, which is theory of the Poisson process. When events occur randomly, independently of one another, and with an average rate that doesn't change over time, the number of events counted in a certain time interval follow a Poisson distribution. We understand this better. A Poisson distribution is a tool that helps to predict the probability of certain events happening when you know how often the event has occurred. That means the Poisson distribution works with historical knowledge, meaning that we have an idea of how often the events have been occurring in the past, and now we use it to predict the probability of the event happening further on in the future. It is the probability of a given number of events happening in a fixed interval of time. The interval of time is fixed, and we find the probability of those events happening in that interval. Poisson distribution is a distribution that results from a Poisson process. So for a statistical process to be called the Poisson process, it must meet certain criteria. In reality, a lot of processes that we model as a Poisson process don't exactly meet these criteria to a T. They don't meet them perfectly, but we still describe them just for the sake of theory. So what are these criteria? Criteria 1, events are independent of each other. That means the occurrence of one event does not affect the probability that another event will occur. They are not connected at all. They are mutually exclusive. One event does not affect the probability of the other occurring. The average rate, that events per time period or events per interval, is constant. That is the second criteria. And criteria 3, 2 events cannot occur at the same time. Now that we've listed out these criteria, let's go back to the slide with the criteria. Now that they've been listed out, before we go into an example of a situation that can be called a Poisson process, let's discuss briefly a situation that is not the Poisson process. One very, very familiar situation is the spread of COVID-19. We say that for a situation to be called the Poisson process, the occurrence of events must be independent. Is the spread of COVID independent? No, of course not. An infectious disease can never be independent because, well, it is infectious. The probability of getting infected by COVID depends on how close you are to someone with the virus or how widespread it is in your vicinity. The more widespread it is in an area, the more likely a person gets the virus. So it is not independent. COVID spread doesn't satisfy criteria 1. Also, the average occurrence of COVID cases per region isn't constant. So we can't accept criteria 2 either. What of criteria 3? We all know it's quite possible for 2 cases of COVID to occur at the same time. So criteria 3 is also not satisfied. Let's go to the next slide and discuss an example of a situation that could be modeled as a Poisson process. That's slide 5. For example, suppose we own a website and we observe that the servers go down on average once every 60 days, once per 60 days. But one failure doesn't affect the probability of the next. That means the failures are independent. Maybe there is one fault that happened at one time and a completely different fault occurred at another time. So they are independent faults. They are independent downtimes of servers. All we know is the average time between failures. This is a Poisson process because the occurrence of events, that is the server downtimes, are independent of each other, which satisfies criteria 1. The average events per time period, which is one downtime per 60 days, is constant, which is criteria 2. And 2 events or downtimes cannot occur at the same time, which satisfies criteria 3. Now, if we look at the image below, there illustrates server downtime occurring on average once every 60 days. One happens here on day 55, another happens on day 145, another happens on another day, another day, another day. If you take the average, you see it occurs once every 60 days. And we see again that two downtimes occur at the same time. Yeah, it happens once, not simultaneously, or just one fault on this day, another one fault on this day, another fault on this day. It's all separate days, they do not occur simultaneously. So this depicts a situation that can be modeled as a Poisson process. Now we've discussed an example of what is not a Poisson process, which you are very familiar with, COVID-19, and we've discussed another which can be modeled as a Poisson process, which is server downtime, for which we know the average time between failures. I know this example is not biological, it's not related to biostatistics, but as we go on further in the module, we'll see examples of the use case. We just wanted to use this as a groundwork for our understanding our knowledge of Poisson distribution. Now on to the next slide, the relationship between Poisson and other distributions. We know that the other distributions like the binomial, the Gaussian or normal distribution, and the exponential distribution. Now these distributions have relationships, they have their differences as well as what connects them. As discrete probability functions, the normal and Poisson distribution functions are similar in that they both count discrete events and the events are assumed to be independent. The difference between the two is that binomial distribution describes the distribution of binary data from a finite sample. Hence, it gives the probability of getting k events from n trials, while Poisson distribution describes the distribution of discrete data from an infinite sample. Hence, gives the probability of getting k events in infinite trials. The Poisson is a limiting case of the binomial when n approaches infinity and the probability of success p is very small. In practice, Poisson can be used when n, which is the number of trials, is greater than or equal to 20, and when p, the probability of success or of occurring, is less than or equal to 0.05. That means we have a large number of trials, but we have a small number of success. This property of Poisson distribution makes it suitable for modeling events of occurrences that will happen a large number of times, but still happen rarely due to the infinite nature of sample space or trials. For lambda, which we will discuss later on, greater than 1,000, a normal approximation, which is the normal distribution, can be used with mean equals to variance, which is equal to lambda. The exponential distribution deals with the time between occurrences of successive events as time flows by continuously. Hence, it describes the time between events in a Poisson process. The exponential distribution describes the time between events in a Poisson distribution. That's the relationship. We'll discuss that further in the waiting time concept. Now, let's move on to a critical aspect of our module, which is called the Poisson distribution formula. The Poisson distribution probability mass function gives the probability of observing k events in a time period given the length of the period and the average event per time. Here is the formula that describes what we just said below. This formula is quite complicated, and the event over time times time period is usually simplified into a single parameter, lambda, which is this. Lambda is called the rate parameter. With this substitution, the Poisson distribution probability function now has one parameter. And so we can mathematically describe the Poisson formula as the probability of k events in an interval is equal to e raised to the power of minus lambda times the ratio of lambda raised to the power k to k factorial, which is stated here below. Poisson distribution probability of k events in an interval. Now, what are these letters or Greek letters stated in this formula? K is the number of events in a given interval, which you're already familiar with. E is called Euler's number, one of the most important numbers in mathematics, and it's approximately 2.718282. That number is much longer, but for the sake of simplification, we leave it to 6 decimal places. Euler's number is approximately 2.718282. And lambda, which you're already familiar with, is the rate parameter of the distribution. We say k follows a Poisson distribution with parameter lambda. Let's note something here. Poisson processes are generally associated with time. We usually say events per time period, number of occurrences in a given time. But they do not have to be so. An example of such a Poisson process is the number of trees in an acre. The number of trees, that in this case, is the number of events, while the interval is in per acre. So number of trees in an acre is the events per area, number of trees per acre. So we can say events per interval instead. That covers the entire thing, rather than sticking to events per time period. Now let's further discuss the rate parameter. As we change the rate parameter, we change the probability of seeing different number of events in one interval. Think about it. Let's say we have two buildings, building A and building B, side by side. If 5 people enter building A per minute, that's the rate parameter for A is 5. And 2 people enter building B per minute, that is the rate parameter for building B is 2. Which building has a higher probability of more people entering per time period? Building A, of course, because the rate parameter, the rate at which events occur per interval, is higher in building A. We have more events per interval. So we see that, that depending on the rate parameter, the probability of seeing different number of events either increases or decreases. The below graph is the probability mass function of the Poisson distribution showing the probability of a number of events occurring in an interval with different rate parameters. Now, as you can see here, as the lambda grows, lambda 1 to 2, 3, 4, 5, as the lambda grows, the probability of seeing events by time period increases. At lambda 1, the probability of seeing only one event is as its highest. At lambda 2, likewise, and up to lambda 5. When lambda is equal to 5, the raised parameter is equal to 5, the probability of seeing 5 events is at its highest. And then probability of seeing more than 5 or less than 4 or less than 5, continues to decrease. So depending on the raised parameter, the highest, do you get the highest probability? If you have a raised parameter of 5, your highest probability of events is 5. If you have a raised parameter of 3, the highest probability of events is 3. So the most likely number of events in the interval for each curve is the rate parameter. This makes sense because this parameter is the expected number of events in the interval. And therefore, when it's an integer, this parameter will be the number of events with the greatest probability. So let's move on to the worked examples to better understand this formula. So example 1. Births in a hospital occur randomly at an average rate of 1.8 births per hour. What is the probability of observing 4 births in a given hour at this hospital? From this example, we can clearly see what K represents and what lambda represents. So we say let K be equal to number of births in a given hour and mean rate or rate parameter lambda be equal to 1.8. Hope you understand that. We can now use the formula to calculate the probability of observing exactly 4 births in a given hour. If we go back to our formula, we can plug in where lambda is and where K is. Remember, the formula is exponential raised to power minus lambda. Lambda is power K over K factorial. So this is lambda plugged in here, lambda plugged in here, raised to power K over K lambda. And that this question, the first part of the question, is solved here. Probability of observing 4 births in a given hour equals to 0.0723, which is the same as 7.23%. Now on to a more tricky question. What about the probability of observing 2 or more births in a given hour at the hospital? Observing 2 or more births. So we want the probability of observing where K equals to or greater than 2. That means probability of K equals 2 plus probability of K equals 3 plus probability of K equals 4, so on to infinity. That's an infinite number of probabilities to calculate. And we know that's a rigorous and virtually impossible task. So instead, we calculate the probability of observing less than 2 births per hour and subtract it from 1. What's the logic behind that? Basically, we are applying the concept of complementary probability. Just in case you're not familiar with that concept, let's remind ourselves of it. 2 events are said to be complementary when one event occurs if and only if the other does not. The probabilities of 2 complementary events add up to 1. That's why I'm subtracting it from 1. For example, rolling a 5 or greater and rolling a 4 or less on a die are complementary events because a roll is 5 or greater if and only if it is not 4 or less. So you can't roll a die and it becomes 4 or less or 5 or greater. It's either one or the other. So similarly, in this example here, the probability of observing 2 or more births is complementary to the probability of observing less than 2 births. Because at the same interval, we cannot observe 2 or more births and still observe less than 2 births. It is one or the other. They are complementary. So to make things easier for us, we calculate the probability of observing less than 2 births per hour, since it's easier to calculate, and then subtract it from 1 to get the probability of observing 2 or more births. And that is what is mathematically depicted here. As you can see, the probability of observing less than 2 birds is the same as the probability of observing 0 birds here. Observing 0 birds plus the probability of observing a single bird. Hope that makes sense. The probability of observing less than 2 birds. See here, because it's the sum of observing probability of 0 birds and observing the probability of 1 bird. Then subtract it from 1 to give us probability of observing 2 or more birds. So we basically use in a situation where we have to find the probability of in a very, very large K, we can use complements. We can use the concept of complementary probability. And in this example, we get 0.537 of 53.7%. That is probability of observing 2 or more birds in a given hour at the hospital is 53.7%. Hopefully that makes sense. Just think about it a little bit, look through the examples, and sure enough, you'll see a bit of sense in it. So let's move on to the next example. Example 2. Suppose there's a disease whose average incidence is 2 per million people. What is the probability that a city of 1 million people has at least twice the average incidence? Twice the average incidence would be 4 cases. Let's try to wrap our heads around this. Since the average incidence is 2, twice the average incidence will be 4, because twice of 2 times 2 will be equal to 4. So at least twice the average will be 4 or more cases. So we can easily suppose that the random variable k equals number of cases in 1 million people, and lambda equals to 2. And here, so to find the probability of 4 or more cases, remember that this could also be a very rigorous process. We are going to find the probability of 4 cases, 5 cases, 6, 7, up to infinity. So we take the complement, and in this case, the complement with the probability of 3 or more, 3 or less, sorry, or less than 4. So subtract 1 minus the probability of 3 or less cases happening per million people. And this is how we solve it. Probability of 0 cases, probability of 1, probability of 2, and probability of 3 cases. We sum up those probabilities and subtract this from 1, just as we did in the previous example through the complementary probability concept. And then we get 0.143 or 14.3 as the probability of at least twice the average incidence. That's 4 or more cases per million people, 14.3%. So these examples are clear. If you don't get them, you can always go reread and reread them, and it will stick. In a Poisson distribution, the mean and variance are equal to the rate parameter lambda, while the standard deviation is equal to the square root of lambda. Remember that standard deviation equals to the square root of variance. And in a Poisson distribution, we say that variance is equal to lambda. So we can reasonably say that standard deviation equals to square root of lambda, the raised parameter. This means that the coefficient of variation, the ratio of the standard deviation to the mean, is CV, which is coefficient of variation, equals to standard deviation over mean, which is equal to the square root of lambda over lambda, which is equal to 1 over the square root of lambda, or the raised parameter. So just to be clear, coefficient of variation equals to 1 over the square root of the rate parameter. The coefficient of variation is dimensionless. It has no dimensions. So it is used in comparing the scatter or the variation, the scatter, as the variation of variables measured in different units. We are not concerned about units in concept of variation because it's dimensionless. So it is very useful when you're trying to compare the variability of two different features or variables. You could ask, for example, whether the variation in pulse rate is greater than or less than the variation in the concentration of serum sodium. The pulse rate and sodium are measured in completely different units. You see here, the pulse rate and sodium are measured in completely different units. So when we compare their standard deviation, it will make no sense. And this is where the coefficient of variation becomes useful. Because comparing the coefficient of variation will be useful to someone studying homeostasis. That is an example of using the coefficient of variation in biostatistics. In the next module, we'll also discuss further use of the Poisson distribution in biostatistics. Well, this module is indeed under the biostatistics subject. So we have to dedicate a bit of our discussion to examples or use cases of Poisson distribution in biostatistics. So the Poisson distribution is used to describe the distribution of rare events in a large population that's already established. For example, in cell biology, at any particular time, there is a certain probability that a particular cell within a large population of cells will acquire a mutation. Mutation acquisition is a rare event. If the large population of cells is divided into smaller cultures, as is done in the fluctuation test, the Poisson distribution can be used to determine the probability that any particular small culture will contain a mutated cell. A mutated cell in this case is the occurrence of the event, while the small cultures that were divided are the intervals. So probability of finding a mutated cell in a small culture, in an interval of a small culture, can be described by a Poisson distribution. Of course, there are other examples of Poisson processes in biostatistics and epidemiology. So we'll list some of them out. One is the proportion of cells that will be infected at a given multiplicity of infection. Another is the number of bacteria in a certain amount of liquid. Another is the number of mutations in a given stretch of DNA after a certain amount of radiation. Another example is the number of mutations on a strand of DNA per unit length. Number of mutations per unit length. Sounds like Poisson distribution, doesn't it? The number of individuals, the particular rare disease per area. An example of that disease can be something like spina bifida, but not Ebola because it's infectious. Remember, we already acknowledged that infectious diseases can be modeled as Poisson processes because they are not independent. Probability of occurrences are affected by each other due to them being infectious. So these are some examples or some use cases of the Poisson distribution in biostatistics. Now we move on to another subtopic, which is the waiting time concept. The waiting time concept. An intriguing part of a Poisson process involves figuring out how long we have to wait until the next event. And this is sometimes called the inter-arrival time. Let's consider the situation. In a cafe, customers arrive once every 12 minutes. If we arrive at a random time, and we know that customers arrive once every 12 minutes, How long do we think we have to wait to see the next customer? We won't go into the derivation because it comes from a probability mass function equation, and that is outside the scope of this module. But the time we can expect to wait between events is a decaying exponential. The probability of waiting a given amount of time between successive events decreases exponentially as the time increases. I repeat that. The probability of waiting a given amount of time between successive events decreases exponentially as the time increases. The following equation shows the probability of waiting more than a specified time. So here it is stated in this formula, probability that your waiting time is greater than a specified time. Waiting time, uppercase T, is greater than a specified time, lowercase t, equals to the exponent of minus lambda times t, the specified time, lowercase t. In this equation, lambda, of course, is the raised parameter, which you're already familiar with, and t, as we stated, is the specified time, lowercase t. In the example, we have one customer every 12 minutes, and we specify that the next customer will arrive at time t of 6 minutes. If we plug in the numbers, then the probability that our waiting time, uppercase t, is greater than that specified time of 6 minutes, equals to the exponent of minus 0.083 times 6, which is equal to 0.607. So we get a 60.7% chance of waiting more than 6 minutes. This equation also implies that the wait time of a Poisson process can be described by an exponential distribution. But let's go back. I hope you know why our lambda 0.08 is equal to 0.083. That's because we said we have one customer every 12 minutes as our raised parameter. In decimal, it is 0.083. I hope that is cleared up. So this equation implies that the wait time of a Poisson process can be described by an exponential distribution. The waiting times between events are memoryless. So the time between two events has no effect on the time between any other event. The time between two events has no effect on the time between any other event. This memoryless behavior is also known as the Markov property. So any process that has this property is known as a Markov chain. And the Markov chain is a simple concept which can explain most complicated real-time processes like speech recognition, text identifiers, path recognition, and many other artificial intelligence tools. So it is a simple but important concept which is also applied here in Poisson distribution, but discussing it is also outside the scope of this module. But let us have it in mind that the memoryless behavior of our waiting time in the Poisson distribution is also known as the Markov property. Remember, we said that the probability of waiting a given amount of time between successive events decreases exponentially as the time increases. So in this slide, we have a graph that helps us to visualize the exponential decay of waiting time. Look at the graph decays exponentially. It first starts gradually, then with time it increases by larger margins and decreases there, continuously decreases. So there's a 100% chance of waiting more than 0 minutes, which drops off to a near 0% chance of waiting more than 80 minutes. So the longer the waiting time, the lower the probability that we wait longer than a specified time t. If our waiting time is shorter, then we have a probability that it will be longer than the specified time or greater than the specified time. But as the waiting time increases, the waiting time, package T increases, the probability starts to drop exponentially. And that is what this graph helps us to visualize. This basically is a short explanation or discussion of the waiting time concept. So now we move on to exercises. We have some exercises for you to gauge your knowledge of what we've discussed about Poisson distribution so far. So there are 3 exercises here. Number 1, assume that bacteria of a species called X. I don't think there are any bacteria species actually called X, but we'll just give an arbitrary name X to a species of bacteria. So assume that bacterial species called X are randomly distributed in a certain river Y, an arbitrary name for a river, according to the Poisson distribution with an average concentration of 16 per 14 milliliters of water. If we draw 10 milliliters of water from the river using a test tube, what is the approximate probability that the number of bacteria X in the sample is exactly 4? This could be a little tricky, so we'll give you a hint. The rate parameter lambda, remember the very first equation that we wrote is the event over the interval and the specific interval. So the event, we have to find that out, the interval, and for this particular question, the specific interval. When we put all this together, we'll get what our rate parameter is. Question 2. If a random variable X obeys the Poisson distribution with mean equals to, what is its variance, rate parameter lambda, and coefficient of variation CV? Remember, we also discussed what the statistical parameters are in Poisson distribution. Question 3. Suppose the probability of suffering a fever from a flu vaccine is 0.005. If 1,000 people are given the vaccine, use the Poisson distribution to approximate the probability that A, 1 person suffers a fever as a result, and B, more than 3 people suffer a fever as a result. These are the 3 exercises that have been read out. We'll give you a few minutes to solve them. Just don't panic. Just open your mind to what has been discussed over the past 30 to 35 minutes so far. Get the brains working. See this icon here? You can see the gears moving in the head, brain. So just get it together and try to solve it. You have a few minutes to do that. Around 5 minutes, after which we'll look at the solutions in the next slide. Hope we're getting the hang of it. In a minute, we'll look at the solutions. Okay, let's look at the solutions to the exercises. So now we'll be looking at the solution to the exercises. Yeah, these are the solutions for the 3 questions 1 to 3. Last one is here. So for question 1, the solution. If we notice, we left the int for question 1. The int is very important in solving this question because that is what you need to work on first to get the rate parameter, which is our event per interval. Now we still are the average concentration, which is for that body of water. So the general event per interval for that body of water is 16 per 40, which is same thing as saying 16 divided by 40, right? But in this case, the interval we're actually interested in is 10 milliliters, not 40 milliliters of water. So using that formula we entered that, which is this formula, the rate parameter becomes, as we stated here, the event, the specific interval we're interested in, which is 10, multiplied by the general event per interval, which is 16 over 40. And that will give us 4. So I repeat, using that formula, we entered that the rate parameter becomes the event 16 divided by interval 40, then multiplied by the specific interval 10. Solving that gives us a rate parameter of 4. And then we can now find the probability that the number of bacteria X in the sample is 4. In this case now, our X and K are equal to 4. So we can just plug in the formula. Remember the formula? Poisson distribution formula. Then we said lambda raised to power K, or in this instance, X over X factorial multiplied by exponential, or the Euler's number raised to power minus lambda. So that's 4 raised to power 4 over 4 factorial times Euler's number raised to the power of minus 4. Very easy in this case to plug in the numbers. And that gives us 0.195 on 19.5%. So if I use the number of bacteria X in the sample, which is 10 milliliters of water, is 0.195 on 19.5%. Hope you understood that hint. So let's say you're giving a general event per interval, but they ask you to now give you a new interval to find this parameter. You multiply that general interval, general rate parameter, which is the event per interval, times that specific interval you have to work with. So the solution to question 2 is actually quite straightforward. If you recall that the mean, the variance, and the rate parameter lambda are all equal in a Poisson distribution. So for a Poisson distribution with the mean equals to 2, the variance will also be equal to 2, and the rate parameter lambda will be equal to 2. So we've solved the first part of it. And now to find the coefficient of variation, CV. Remember, in earlier slide, you said our coefficient of variation is the ratio of our standard deviation to to the mean. Standard deviation is the square root of this parameter, and the mean is equal to the raised parameter. So all in all, this coefficient of variation is equal to 1 over the square root of lambda, or 1 over the square root of the raised parameter. We already found the raised parameter to be equal to 2. So 1 over the square root of 2, which is equal to 0.707. So the coefficient of variation is equal to 0.707. That's the solution to question 2. And finally, question 3. Here we have to find the probability that one person suffers a fever as a result of the vaccine. In this case, remember we used in the first solution where we multiplied by a specific interval equals to 4. In this case too, we multiplied 1000 times the 0.005, which is equal to the raised parameter of 5. In this case, to get this parameter, we multiply the probability of suffering a flu fever times the 1000 people we are giving, which is this is like a general event per interval 0.005. But in this case, we are interested in 1000 people. So we do what we did in example 1, exercise 1, by multiplying this event per interval times the specific interval we are interested in, which is 1000 people in this case. So 1000 times 0.005, which is equal to 5, will give us the raised parameter in 1000 people. So the probability of one person suffering a fever, probability of K being equal to 1, remember the formula, we plug in, so it will equal to 5 raised to power 1 over 1 factorial times Euler's number raised to power minus 5, which gives us 0.0337 or 3.37%. Now to find to find the solution to the B part of the question 3, to find the probability of more than 3 people suffering from a fever, we find the probability of 3 people suffering from a fever, and then subtract the probability from 1. Remember we did that, the concept of complementary probability. To find 3 people, 4, 5 to infinity is rigorous. So we find probability of 3 people, only 3 people, a probability of 0, 1, 2, and 3. We add them up, their probabilities up, and subtract it from 1, just as we did here. And we get 0.735 or 73.5%. We're just using the concept of probability, the concept of complementary probability, just as we did in the examples we looked at in the earlier slides. So these are the solutions to the 3 exercises. You can look them up over and over to get the hang of it. They are pretty straightforward and easy to understand. So those are the solutions. It's okay if you didn't get all of them correctly, or if you didn't get any at all. The important thing is you made a decent attempt at the questions. Remember, practice makes perfect. And as long as you keep studying and practicing, soon enough, you may just become perfect at Poisson distribution. Next, we summarize this module. So, to summarize, we'll be looking at 3 key takeaways from this topic. The first key point is this. For events to follow a Poisson distribution, they must meet certain criteria. Remember, we said that a lot of times, some of the situations we model as Poisson processes do not strictly follow these criteria, but these are the 3 criteria. First, events must be independent of each other. One event does not affect the other. That's what we mean. The average rate of event occurrence is constant. And the third criteria, 2 events cannot occur at the same time. Poisson distribution describes events that occur rarely in a relatively large interval. There's a large interval for its occurrence, and those occurrences happen rarely. Poisson distribution models those type of situations. The second key point, a Poisson distribution can be mathematically described with the equation probability of K per interval equals to Euler's number raised to the power minus lambda times lambda raised to the power k over k factorial, where we said the where we say lambda is equal to the raised parameter, and which is equal to the mean and variance of the distribution. And Euler's number E is approximately 2.718282. 2.718282. And the third and final key point, the waiting time of a Poisson distribution can be described with the equation probability that the waiting time uppercase T is greater than a specified time T is equal to Euler's number raised to the power minus lambda T. This equation here implies that the wait time of a Poisson process can be described by an exponential distribution. These are the three key points we would like to remember from this module. Now, for more information on this topic, Poisson distribution, we have some references listed here. If you notice the first one by Ait Frank, Handbook of the Poisson distribution, it was published in New York by John Wiley and Sons. If we go back here, we see that it was published in 1967. This goes to show how old the concept of probability distribution is. So you can imagine the wide application it will have had over years in various disciplines, including biostatistics, or what groundbreaking knowledge this distribution could have opened up. The other reference materials you can look at, some more advanced than the others. We have the Poisson distribution and Poisson processes explained. It's an article written in towards data science online publishing website by Caution William. We also have others like found in the probability and statistics with R. Those are books written that have discussed the Poisson distribution. There are still a few others listed here. So in case you want added information, you can always look up these materials. So it was nice sharing the knowledge of Poisson distribution with you. Hope you enjoyed this presentation and learned a lot. A big thank you. Bye.